In a world where programming language research matters, three scientists have set up to answer a long-standing question on the expressiveness of programming languages, with Marco Patrignani from Stanford and CISPA, Eric Martin from Stanford, and Dominique Devriese from VU Brussels. This winter comes on the Semantic Expressiveness of Recursive Types.
I'm implementing my own language, and I'm adding recursive types to it. Which formulation should I choose? Is there one that is more expressive?
I'm teaching a class on recursive types, so what should I tell the students? Is there a formulation that is more expressive?
In our work, we provide an answer to these questions, and we prove that isorecursive and co-inductive equirecursive types have the same semantic expressiveness. Additionally, we also prove that they are semantically as expressive as just adding a fixed point operator to the language. To compare language expressiveness, we rely on the notion of fully abstract compilation. We prove that the canonical compilers between these languages are fully abstract, and from this we conclude that the languages are equivalently expressive from a semantics perspective. We will now see how this theory works once applied to the source of the compiler being the simply typed lambda calculus with isorecursive types, which is in red, and the target of the compiler, so the output of the compiler, being the simply typed lambda calculus with co-inductive equirecursive types, which is in pink. Fully abstract compilation is about reasoning about the interactions of two terms and their compiled counterparts with contexts in two different languages. Intuitively, contexts C are larger programs that the terms interact with. We need to reason about the interactions over the possible interfaces that the languages allow. In this case, the source interactions happen over a possibly isorecursively typed interface, while the ones in the target happen over a possibly co-inductively equirecursively typed interface. By proving the canonical compiler is fully abstract, we are effectively taking the same term in the two languages and proving that all interactions over an interface in ISO are expressible as interactions over an interface in equi and vice versa. From this we can conclude that ISO and equi are equivalently expressive from a semantics perspective. Proving fully abstract compilation is non-trivial, and our setting is made interesting, but at the same time also complicated further by having co-inductive derivations.
There is an optimal way to prove this.
We have to build an approximate back translation and use an asymmetric logical relation. I'm on it.
First, we rely on a relatively recent proof technique called approximate back translation. In the proof of fully abstract compilation, there's a step at some point that we'll see later where we are given an equicontext to reason about in the ISO language. And in order to express it, we rely on a back translation function which goes the opposite way of a compiler, but it's not necessarily the inverse of compilation. We cannot back translate the equicontext based on its syntax, otherwise we lose all type information, so we back translate it based on its type derivation. However, this derivation may be infinite as it may include a co-inductive type equality derivation. The key bit we rely on to address this concern is the approximation index n. Intuitively, for fully abstract compilation, we reason about contextual equivalence, which observes differentiation, that is, eventually things terminate in some number of steps n. So even if we have recursive types that are proven equivalent, it is sufficient to use an nth level unfolding of those recursive types because we know the equiterms terminated in n steps, so they cannot have unfolded the recursive type more than n times. Second, we need a cross-language step-indexed asymmetric logical relation that tells us that if one of the two related terms terminates, so does the other. We require that a term and its compilation, as well as a context and its back translation, are related in both directions. A careful, but in this case standard setup of the logical approximation is sufficient to guarantee that knowing that the equicontext with compile T1 terminates, we know that the back translated context with ISO T1 terminates. So by ISO contextual equivalence, we know that the back translated context with T2 terminate in some steps. And by using the other direction of the logical approximation, we get to know that the original equicontext with compile T2 also terminates. This lets us conclude the hard part of full abstraction and therefore our result.